Is this on? Hello, everyone. Everything was practically said. I'm supposed to welcome you to the second day of Ghost Day. And seeing how the second day of Ghost Day sounds, I'm afraid the organizers will have to rethink their name, because if they're going to keep up doing so many good talks, it might become a ghost weekend or even a ghost week. So a virtual round of applause for the organizers for a great conference so far. And I'm here to introduce Karol Kurach, PhD. He got his PhD from the University of Warsaw, where he was collaborating from people from the Brain Project and OpenAI. He later became responsible for giving us practical ML features in Gmail, such as the Smart Reply or the tabs. He's now part of Cosmos, where he is helping retailers catch their customers in the virtual world. So I believe he's more than well equipped to talk about today's topic, which is the habits of highly effective ML practitioners. So without further ado, let's take it away.
All right, so hey everyone, my name is Karol Kurach, and today I'm gonna tell you about 7 habits of effective machine learning practitioners. So before we start, a few words about me. So I did my PhD in machine learning at University of Warsaw, specializing in recurrent neural networks with external memory. My original background is in computer science, and in particular, I really enjoyed the competitive programming, and I did a lot of that during my high school and master's studies. I spent last 8 years at Google working in various research teams. So for the first few years, I was a member of Gmail Intelligence. So this is a research team, but embedded within the product. So that means basically that you can research anything you want, as long as it's helping Gmail in some way. So, it's focusing on text methods, etc. After that, I switched to Google Brain, which is a pure research team. And the main difference between pure research team and product team is that in pure research, you can really focus on those goals that maybe research goals that can be useful few years from now. It doesn't have to have immediate translation to the existing product. Very recently, actually this year, I left Google and I joined a Polish startup, Cosmos, which tries to understand the world of shopping. So I believe that given my background from product teams, pure research teams, and also now from the startup, I hope I can give some useful advice about practical machine learning. So what is this presentation really about? So this is a conference about applied machine learning, so I really wanted to focus on those good practices in applied machine learning. I guess many of you are still doing your studies and doing machine learning classes. Maybe some of you are competing in machine learning competitions such as Kaggle, or maybe even tried to read and reproduce actual research papers. So in all of those places, you're usually given a very well-defined problem with nice metric to optimize, with data sets that are ready to use and clean. And really your main challenge is to find a clever model that solves the problem with the highest possible accuracy. So this is what I call the textbook machine learning. And the thing is, all of those fancy models is only a small part of the work of a real researcher when you really want to create a practical machine learning solution. And my estimate is that it's maybe between 5 to 10% of actual work. So in real world, the problem is very often unclear, or it can even change over time. You may get some data, but it's very messy, it's missing values, it may be in very different formats that you have to unify, it may be totally inconsistent or have strange outliers. On top of that, it's also very often that the business metric that you would like to optimize can be easily computed. So, for example, imagine you would like to create a system that would respond that would create good responses to emails. So how do you judge it? What is a good response to an email? On the other hand, even if you know how to compute this metric, sometimes obtaining the ground truth may be very costly. So let's say you would like to create a model to predict how many people visited a store. How do you know if the model is doing well? You could send people to count people coming in and out to the shop, but obviously this type of evaluation doesn't scale really well. So you might need to invent a proxy to judge your models. So yeah, all in all, the main challenge of a real world system is to actually get it to work. So how machine learning practitioners approach it? I wanted to share with you a set of habits that, in my opinion, can vastly improve the odds of your system being a success. And the next slide contains, in my opinion, the biggest secret of all successful machine learning practitioners that I know. And before I move to the slide, I just wanted to warn you. So, you know, what's seen can be unseen. And like Morpheus from the Matrix movie, I can offer you only the truth. So if you're a student and you like to improve your accuracy on tiny and clean data sets, please don't watch this presentation any further. And for the rest of you, you have been warned. So the biggest secret of successful machine learning engineer is to actually solve the problem without machine learning at all. So it might seem surprising, right? But in many cases, what you really need is a bunch of heuristics that can get you very far. So things that usually work very well in practice are stuff like regular expressions, bunch of if-else statements, whitelisting, some customly added rules based on counting, etc. To give you one motivational example, I wanted to mention one system that I worked more on. So in Gmail, there is this thing called Smart Reply. Maybe you notice it in Gmail. So this system takes an email and classifies it into one of few categories, such as promotional or personal updates, etc. And when we launched the system for the first time, it didn't have any components at all, and nevertheless, it was a big success. So it consisted of multiple different components. So, like, you know, we had a list with things like, oh, if this email is from Facebook, then it's social, or maybe if it's from Amazon and contains word received, then it's a purchase type. We also had some counters for different addresses and domains. So, for example, we could count how many messages a given address sent versus receives. So this could indicate that, like, you know, if it sends a lot but doesn't receive a lot, that may be a promotional email, for example. So what's nice about this kind of rule-based system is much easier to debug and maintain, and allows for much quicker iterations, because all the logic is in the code. Everyone can easily read it and also easily write a test for that. So the life is simple. Another good reason for which you may want to use a non-ML solution is that you just simply don't have the data to train, or the data you have is extremely limited. So going back to the previous example, in the beginning, we didn't have like any training set at all. We didn't have something that would tell us, yeah, this kind of email is promotional or this kind of email is personal. However, by building this first version of this system, we're able to launch it and get the feedbacks from the users. So maybe, you know, in Gmail is this mechanism that you can move email between categories. So you think that, oh, maybe this message was actually not promotional, but it was actually update. And then you can move it. And we use this feedback from our users as a training data to train a new classifier. So it's a completely valid approach that the V0 is without ML, and you cover really those big cases, like 80% or 90% of your use cases. And this whole long tail that you would like to handle with machine learning models, you use the data that you get from your users. So finally, there are kind of problems that are not really well suited for machine learning for various reasons. And I'm not saying they cannot be done. There are people working on them, but I'm just saying if you approach those kind of problems, you really need to know what you are doing, and preferably you are an expert. So like, you know, the free solo climbing. There are people who do this. There are people who are good at it, but definitely you shouldn't try that if you are not well prepared. So those kinds of systems are usually when, like, for example, we need models for which decision needs to be explainable. So imagine you would like to help a surgeon to do the operation. And yeah, it's useful to predict, like it's useful for the surgeon to know not only what to do, but like why the system thinks so. So the surgeon can validate the assumption. There are systems for which we don't want to tolerate big changes between model. So how machine learning models works is that, you know, the accuracy might stay or be better, but all the results can shift drastically. The models don't care about that. And maybe it's not a problem in ads because you care mostly about accuracy, but maybe in a system in which history is important, you don't want to change the history every time you push the new model. Finally, there's also a class of problems that are just better handled by classic algorithms, such as combinatorial optimization. But okay, so let's assume we have the data and our problem is actually suited for machine learning. Then what would be the first step? What would you do? So the most effective people I know, both in research and production systems, will usually start with making a deep dive into the data they have. And I believe it's the second most important habit. So what do they really mean by deep dive? I think of it as a very deep understanding of the data distribution, looking for patterns and various problems with the data. So there are several main components of it, as you can see in the pictures. So there is cleanup. So, you know, you want to remove various outliers. You want to deduplicate the entries in the data. You want to make sure the formats that you have are matching. So, you know, you may be collecting data from the whole world, and maybe in one place you have kilograms, in another place you have pounds, or maybe you have kilometers and miles, or maybe the days that you have are provided in local time zones. So you want to standardize all of that. The next step is normalization, which can very heavily depend on the data type. So for images, you might want to crop or center them. For text, maybe you want to fix typos and change the words into canonical forms. And for signals, maybe you want to do FFT or something else. Finally, for features, you want to identify missing values and think what to do about them. So do you just drop, or maybe you replace with the average of other values? Also, you need to take a look at the feature ranges. So if you want to make sure that you have the correct output. For example, if the predicted output should be in the range of -1 to 1, you shouldn't use SIGMOID, right? So this data exploration and cleaning is really a critical step because it will make all your models work better. And it also can help you because you might notice some of the data imbalances that you would like to address. And it can also give you some ideas of what kind of models could be useful for solving the problem that you have. Another extremely useful thing is to visualize the data. So it's obvious for images and video data sets that you can visualize them, but it can be done for other types of the data too. So here, for example, you have visualized text data set with word embeddings. So plotting 2D points is easy, but how do you plot 100 dimensions word embeddings? So it turns out that there are very useful techniques called dimensionality reductions, such as TSNE or PCA. that you can use to map any n-dimensional vector to 2 or 3 dimensions, which makes it very easy to visualize. And here in the picture, you can see an example of the t-SNE embeddings. And this is very useful because by looking at that, you can figure out, oh, there are some outliers here that they may indicate some problems in your data, or you can look at the clusters and try to tag the whole cluster with some value. And the final thing, and the best you can do about your data, is to get more of it. So there are very different approaches depending on the problem, but here's a few examples. So let's say you want to train some image classifier and you have relatively small data set. So for example, you could take a pre-trained ResNet or other model and just do fine-tuning on top of that. Or maybe you want to train something related to text. So then you could take a public data set of 1 billion words from Google and use it to train something. If you happen to have the data, but you don't have the labels, it might be useful in this scenario to hire people to do the labeling for you. So for example, use the service as Amazon Turk outsource this work. Finally, you can also scrape websites, especially Wikipedia was used for a lot of very interesting research work. All right, so now once you spent quite some time on going through the data and validating it, it's finally time for what? Probably you would think that for doing the models, but actually it's not. So let's move to the habit number 3, which is investing in reproducibility of your work and experiment. So probably you have been many times in the situation that you got some experimental results, but it was effect of rerunning something that already crashed twice, and then you had parameter changes along the way, etc., etc. And it's hard to reproduce. And actually, many of the machine learning pipelines look as the image you see on the right, that, yeah, you need to run this Python script, then maybe run Java, then manually tweak something, and then copy paste, and then finally maybe somehow it works. So the problem is, if it's super hard to reproduce, if people can't reproduce, it actually means that almost that research didn't happen, because you cannot get these results, and other people can't easily contribute and help you improve the model. So there are like several simple rules that can help you to address this problem. So the most basic thing is to use the version control system for your code. So I mean, it's a no-brainer. You should have something like Git or SVN or Mercurial or other stuff, and make sure that whatever code you wrote is really tracked. What were the changes? And the next step is to actually track your experiments with code. So whenever you create an experiment, I like to do this in a way that I have I define each experiment as a set of different flag values, and I commit it in my experimental file. Basically, if I want to run something, this is a committed code, and I can run, I can see the results, and I can always go back to it. It's also, from my experience, very useful to keep track of local modifications. So if you have something like Git, you know that you don't have to commit the changes, but somehow some of the changes can be not committed. So it can be useful to also export the difference between head and your local changes to some place where you track the experiment output. So you can later make sure that you really run what you thought you were running. Okay, so now that we track changes to our model code and parameters that we use in experiments, the next step would be to add some kind of tracking to our data changes. So, there could be a situation that you are doing experiments with some data sets, and then, for example, you notice a bug that you incorrectly convert pounds to kilograms or similar. Or maybe you would like just to have a simpler version of your data sets with only a subset of classes that would allow you for a faster iteration. One of my favorite solutions for such use cases is keeping all training data as TensorFlow datasets. This framework allows you to make sure that you have a standardized interface for all your models. It can take care of fetching data from various locations, and it allows you to have different versions. So you can look at this code snippet, how it works. So basically, you can very easily load it, run some standard operations like batching, shuffling, prefetching, etc. And then, like, whenever you decide to, for example, change the preprocessing, you can just update the version and you would load it as MNIST v2 or something. And yeah, you can also use it for very quickly accessing popular research datasets because they are already integrated in TensorFlow datasets. And by the way, it also works with PyTorch. Okay, so finally, once our code and data is nicely tracked, let's think how we can track the output of our experimental runs. First of all, I believe the most important thing here is that we use one standardized code for evaluation of different submissions. So, you know, if you have a research team or like students group, etc., you don't want every author of model to implement their own evaluation. You want like one system that you can send to, you can trust, and it will give you just some number how the model is performing. And in my opinion, it's also very convenient to have this dashboard on which you can see, yeah, which commit it was from Git or what parameters were used, what were the scores. You can sort that, search by it, etc., etc. So there are many options available for such tools, and yeah, you can search in the internet. But to give you one example, at Cosmos we use MLflow, which is a simple and open source system that can provide all of this functionality. So you can integrate it, and it almost works out of the box. Okay, so once we investigated the data and prepared ourselves a good reproducible setup, now it's time for the next step, which is trying some trivial baselines. And this is the fourth habit of successful machine learning practitioners. So why simple models? I mean, it's kind of obvious. So, you know, the first reason is you want to do the end-to-end test of your whole training pipeline. You want something that's easy to debug. So think of something like linear regression or maybe some tiny convolutional network. You want to run the training on that. You want to visualize all the metrics. You need to make sure that if you want to later run inference, all of this works. So another point is that such a simple model, it's also a good comparison with your previous handcrafted heuristics, and it's also a good point for, like, good reference point for all future models. And really, the main principle is to keep it as simple as possible. While training those very simple baseline, there are a few things that can make your life easier. So, for example, you may want to fix a random seed to make sure that once you run the code twice, you will get the same outcome. You may want to disable all data augmentations. I mean, they will be useful later when you want to regularize, but now it's just opportunity for getting more bugs. And the same goes for all other techniques that you can think of, like, you know, don't add dropout, don't add batch normalization. Basically, try to make it really, really simple. And it's a good idea to use some well-tested optimizer, like Adam, for example, with default parameters. There is much more advice on keeping it simple on Andrei Karpathy's blog, and I totally recommend you to read it. The link will be on the last slide. One simple test to make sure that everything looks good is that you can try to get your model to overfit a batch of training data. So the way you do this is basically you fix one batch of the data, and you try to increase the capacity of the model, and you try to reach the lowest possible loss, like 0, for example. And this can show you that all the losses and training is set up correctly, and you have enough capacity with your model. Later, when you decide to add more stuff, like maybe the mentioned augmentation or dropout, etc., remember to add only, like really, only one thing at the time, because otherwise it can get messy again. Okay, so let's recap. So we are done with investigating the data, our infrastructure for code, for experiment changes, for data changes is in place. We did some very simple baselines. So now it's finally time to, to read the most recent papers, try some cool new state-of-the-art models, like get them, train, and win. Like, correct? Well, almost correct. So before starting to add the new ultra super cool method, efficient machine learning practitioners will usually try to get the code and reproduce the paper results. And probably they will have many doubts when the code isn't available, which is the fifth habit. So maybe you have heard there's a big reproducibility crisis in research in general. There was a recent study by Nature journal in which they asked 1,500 researchers, and it turned out that most of them have some problems with reproducing results from other papers. So why papers might be hard to reproduce? So there may be various reasons, and there is not a lot of hard data on this question, so we can mostly speculate. So I believe that very often it's just like a researcher simply forgetting to mention some detail that is obvious for them, but then it turns out to be very important. Some people are forced to publish because otherwise they won't get their PhDs or they won't have enough publications for getting a grant. So, they might be incentivized to improve their results so that their chances of acceptance are better. Or there are also people who like to send half-baked papers to just plant a flag so that later everyone else who is working on the topic has to cite them. And because of this rush, they could make a bug in the code, don't even notice, and by mistake report a higher score. So this is a speculation. There may be like many reasons why this is happening, but this happens in general, and it's not really specific to computer science or machine learning domain. Luckily for us, especially in machine learning, we have a secret weapon that allows us to check the claims from the paper, and it's the source code. So I wanted to share with you one story of a paper that got very popular. So basically what we did, we took several popular generative adversarial networks and we wanted to compare them fairly. So all of those models claimed to be better than the GANS before them. And the problem was that almost every one of those methods had a slightly different evaluation setup, or maybe used a different architecture, or had a different budget for hyperparameter tuning. So we create a fair comparison, and once we run all of them in this unified setup, it turned out that there is no significant difference between those new methods and the original one, although all of those papers got published and claimed otherwise. So it was even worse when we were working on our follow-up paper, and we looked more at evaluating various GAN normalizations and regularizations. So basically, you would open a paper, and in several of them, there would be a statement like, yeah, we evaluated some metric fresher inception distance using, and we used ResNet architecture, and we used this data set. So, it seems kind of unified. But then once you look at the code, you notice like really lots of differences. So to give you a specific example in this case, like we found 3 different implementations of the same metric returning different results. All but the papers were claiming to use ResNet, but then the design of the ResNet block in the code was different. So the order of layers was different, or when the ReLU was applied. Also, usually the details how the dataset was processed exactly were missing. And one cherry on top is after 3 weeks of debugging one case and like mailing with the authors, we found that the code which was used to write the paper and to generate the results was different than the code which was released online. So, From the paper, it could seem that everything is fine. All of them are using FID metric with ResNet on L-sound bedrooms, but it wasn't at all. So that's why successful and efficient practitioners in machine learning very often like to first check the code and try to reproduce the results from the paper. Only if it works, they would even consider adding this method to their system. So you would probably ask, okay, what if the code is not available? Or, yeah, in our case, what if it doesn't match the paper? So in both cases, I think it's usually best to contact the authors. And I find people in general are very helpful and responsive. Sometimes there might be some problems that their company doesn't allow them to release the code for some reasons, but I would say that's a minority. All right, so once we tested the code to the great state-of-the-art methods and we adapted it to our problem, now it's time for the sixth step, which is tuning. So that should be kind of self-explanatory, but still I think many people just like to check several default values from the paper before concluding that something doesn't work well. And the successful machine learning practitioners spend quite a lot of time tuning their methods. So that's the sixth habit. All right. So, you want to get good results for your method. So what would you do? One natural approach would be to start with the good parameters reported in the paper. If that worked for the author, it should also work well for your method, right? And unfortunately, it's wrong. So, I mean, there might be methods that are robust and they work for many different scenarios well, but in many cases, it's just not true. So the values that you see in the paper may not work for you because, for example, your setup is different. Maybe you used different version of packages. So there was this famous problem in TensorFlow that the resize was working very incorrectly. So if you had like older version of TensorFlow, it might work totally different than like if someone used the newer version in their paper. So I mentioned previously that the implementation details may also matter a lot. So you may implement something differently, and because of that, those values that just simply won't work well for you. I mean, also very often, if you want to apply your model to real-world data set, it might be that simply nobody trained it on this data before you. So you're the first one, and you have to figure out some good values. And there's also some training instability that can affect those values. So what to do? So I think the parameters from the papers are a good starting point. And you can start with them, you can try to play with them, modify by hand in different directions to get a better sense of what might be important. And the next step is to try something more automatic. So what search strategies you could use? So here is a bunch of popular search strategies. So grid search, very popular. And I think in practice, it's mostly useful for various comparisons in papers or different ablation studies. In practice, if you would like to get as good performance as possible from your model, I would always use the random search. So, I mean, it always gets better results than the grid search. And if you would like to improve it even further, there is something called low discrepancy sequences. So it's kind of improved version of random search, where points are quasi-randomly generated in a way that gives some certain guarantees for every parameter axis, so that the biggest gap between checked values is not too big. So you can see this on the picture on the right. So the right column is random search, and the left column is low discrepancy sequences. So basically you can see, for example, for 100 samples, that like, imagine every axis is one parameter. So we have two parameters that we want to tune, X and Y. And for random search, there are like big white spots that were not tested at all. Like, so we don't know what would be the performance of the model in this region. In contrast, those low discrepancy sequences they seem to cover the space much more evenly. So because of that, you may get simply a better model. Other methods such as Bayesian optimization, genetic algorithms, etc., might be useful as well, but I definitely wouldn't start with them. So from my experience, they are usually not dramatically better in practice, and it's always good to keep the system as simple as possible and easy to maintain. All right. So now is the time for the seventh and final habit of efficient machine learning practitioners, which is understand the cost of your solution. Okay, so let's start with the simpler type of cost of the machine learning system, which is the infrastructure. Obviously, when you want to train your model, you will need to get machines. Probably you have heard that some models done by DeepMind, Google Brain, or OpenAI costed millions of dollars just to run the training. And yeah, it's true, all of it. However, even if you don't aim to solve AGI, it can sometimes get quite costly to train multi-layer models on terabytes of data. So really make sure it's worth it. However, while training can be often solved somehow, like, maybe you can run your machine for 2 weeks, or maybe you can do batch processing in off-peak time, which is cheaper. I think what really is much more tricky is the inference. So when you actually need to serve your model. To give you one example, on the right, you can see the inference diagram for Smart Reply, which is a system developed in Gmail with the goal to take an email and generate a response. So normally in a research setup, we would just run LSTM that would predict the response, and we would be happy with that. And actually, that was our first approach. However, it turned out that the cost of running this LSTM was prohibitively high because we were required to generate a response quickly as the mail came. So yeah, basically, it would cost us too much money to run it on every incoming email for this feature to make sense. So what we did, we trained another model with the goal of predicting if the message is likely to have a useful response at all, and we run LSTM only if this model said yes. And because this model was orders of magnitude faster and cheaper, we are able to launch this feature. So, in real world, you sometimes need to do stuff that's maybe that you would normally not do in just a pure research set. And this is the first type of the cost that might be easier to grasp because it maps directly to money. However, there is also another type of cost, which is the maintenance of the system. And so you are probably familiar with the technical debt concept. So machine learning components have all these basic code complexity issues as the normal code, but they also have a larger system-level complexity that can create hidden debts. For example, when you add a new machine learning model to the system, you should consider if it should be retrained. If the answer is yes, it now creates a cascade of things to figure out, like, which system is going to retrain it, how to make sure the model update won't break other parts of the system, etc. Also, having such a machine learning model that depends on some features means that you need to monitor those dependencies, you need to monitor those features, and you also need a backup plan. Like, what your model is going to do if it, for example, relies on some feature that became unavailable because the system that provides it went down, right? On top of that, with machine learning pipelines, they are usually kind of glue between Python, various configs, and other popular production languages such as C++ or Java, which makes it hard to maintain. And very often, this code contains lots of stuff from old and deprecated experiments. So this is only the tip of an iceberg of issues that you get while maintaining the ML system in productions. And if you're interested, and you would like to learn more about the cost of machine learning infrastructure in real world, there is a great paper from NIFS 2014 called Machine Learning, the High Interest Credit Card of Technical Debt. I think this paper captures really well various challenges with deploying and maintaining machine learning models. And despite being over 6 years old, I think it's still very actual. So I totally recommend to read it. It has lots of things that can go wrong with deploying and maintaining the model. All right, and that was the last habit. So let's summarize. The first and most important habit of all is try to launch the system without machine learning. So if you succeed, you are golden. You can also use the data from people interacting with your system to train the next versions. And this time those versions can be machine learning based. The second habit is to make sure that you know your data well. You clean it, normalize it, get familiar with feature distributions, and try visualizing. The third habit is about proper experimental setup. You need to make sure all your models, experiments, and data are tracked. Also, invest in evaluation and keeping track of experiments. The fourth habit is to try most trivial baseline in order to test end-to-end all of your pipelines and make sure you have a stable reference point for all future improvements. The fifth habit that I mentioned is to make sure that before you jump on implementing the newest, coolest, and greatest paper, try to make sure you can reproduce in its original environment with its original data sets. And also keep in mind that the only source of truth that you have is the code. The paper may be missing details, maybe sometimes misleading, or in extreme cases, it may be just wrong. So trust the code. The sixth habit is to make sure your model is tuned properly. If you just want to remember one thing from this point, is just go with standard random search. I think it's good enough for most of the cases. And finally, the seventh habit is a reminder that whatever you do with machine learning, it brings a lot of complexity and dependencies to the system. So you really need to understand it, and you really need to make sure it's worth it. So that's it. I hope you find this list useful. Good luck with making your machine learning models useful and applicable in real world. And I'm happy to take all of the questions. Also, if you'd like to contact me about research, or you would like to work in a startup that takes those machine learning principles seriously, here's my email. So thank you very much.
Okay, so thank you for the very interesting talk. We have quite a few questions. So if you could answer, there's one wise attendee that is asking you if you could share the most interesting metric you had to come up with to score a model, not your usual accuracy, precision, or whatever, but something to test if it really works and the user will be happy.
Okay, so like, first of all, it's worth noting that like when you deploy a production system, it's very rarely a single metric. I mean, it's usually a collection of metrics, at least several of them. And the most interesting, I mean, I can share with you like, okay, what was the metrics, for example, for smart label. So for the system that you classify the mails into the tabs. In this case, the metric was the number of corrections. So like how many times people had to move like one message to a different tab. And then later we figure out that some tabs might have higher importance to people than others. So then we also created like another metric to track that. For smart reply, actually the metric was more or less standard. So we used the click-through rate. So basically the number of times people selected our response versus the number of times we shown the response. But like note that all of those metrics you can compute only once the system is launched, right? So it's a chicken and egg problem. Like you cannot optimize your model on that metric before you launch. So yeah.
Okay, we have a pair of questions that I believe are connected. Jakub asks, when would you use TSNE versus PCA? And another attendee is asking, what about UMAP? You know, the newer version, the new sexy TSNE that's supposed to be faster and better.
Yeah, so personally, I never had performance issues with TSNE, and like, okay, if you have performance issues, the standard way is to get uniform sample of the data and just visualize it, like on the sample. I never used UMAP. I heard it's okay. I don't know, but I heard it's kind of similar to TSNE. But like, I would always choose TSNE over PCA for visualizations. I mean, it's very subjective. It's basically, I did it many times, and usually from PCA you cannot see almost anything, and TSNE actually gives you some nice visualizations, although it has other problems, right? So for example, it's not deterministic, and it doesn't create you this function from n dimensions to, let's say, 2 dimensions. So if you would like to actually use this dimensionality reduction to train the model, then you should go for PCA.
Yeah, because I think it's a difference of what one tool is for dimensionality reduction and the other one is for visualization.
Yeah, makes sense.
Yeah. So we have another question, this time concerning hyperparameter tuning. So the question is, what do you think about high-level tools such as Optuna? I would extend that question to asking you about your thoughts about AutoML, Bayesian optimization methods for searching the hyperparameter space. Have you used those? What are your experiences?
I mean, I use those actually at Google. You have, I don't know, at least a dozen of frameworks like that to tune. One of them, Vizier, I think it's even open source now. So if you go to Google Cloud, there is Vizier Optimizer, and I mean, they work. I mean, they are fine. It all depends on your use case, right? So, for example, I like to understand more my choices. So I like to play with the parameters, see like, okay, which parameters have the bigger impact, and then run something like more based on this gut feeling. And also, like in a production setup, it may be sometimes hard to use this kind of optimizer. So like, you know, when you have one machine, everything is perfect. You see this nice snippet on the web page that, oh yeah, just call our function, optimize, and the world will be beautiful. But then in practice, when you run different, let's say you run a couple of trainings in parallel, each of those trainings maybe uses a mix of machines, like, you know, a mix of like GPU to train the learner and maybe CPUs to train the actors. Like the whole setup is quite complex, and if on top of that you add something else that also chooses the parameters and does stuff, I mean, it just grows the complexity of the system. So I mean, as I said, I usually prefer the simple solutions.
So maybe a follow-up question. You talked about the cost of the model, and part of that being that sometimes you have to retrain the model from time to time. So would you retune a model when you get new data, or do you think it's better to tune the model on the first batch, and then once you get new data and have to retrain, you use the same parameters?
It depends. I mean, usually how it works in production systems such as Gmails, YouTube, etc., is that okay, so we have 2 main strategies, right? So one strategy is like every time you get like a new batch of the data, let's say from the last month, and you train from scratch. The other is you have a learner that runs continuously, and it's just like, you know, every hour it gets some more data, it does some gradients updates, and it's like modifies itself. So when it's continuous learning, obviously it's like the same parameters, it just keep being updated. When you train from scratch, it's usually the case that people refresh on the new data with the same old parameters. And if you want to try new parameters, that would be like a totally separate A/B experiment to run it.
Okay. Sebastian asked, what do you think about the combination of DVC, data version control, and Duck Hub to ensure reproducibility on the data level?
So to be honest, I'm not even sure what's the difference between DVC and things like Git Annex or like GitHub, this large file storage on GitHub, which also allows you to track big files. So like, to be honest, I don't know. I never use it. I mean, if it's open source and it works for you, why not, right? I mean, I prefer like battle-tested, simple technology. So like, yeah, Git Annex sounds like something safe or safer.
Okay, and the last question is from Adam Goncharek, and actually, I wanted to ask a similar question. I think that was not clearly stated in those 7 habits is error analysis. What are your thoughts or takes on error analysis? Do you create eyeball data sets apart from your validation and testing data sets to look if your solution is stable? What are the errors? What's your take on understanding the errors you have from your model?
I mean, usually like the standard approach is like you split into those 3 data sets, right? Like the training, validation, and test. And basically like all the tuning you do on the validation and test you use like really extremely rarely. And that's kind of give you the estimate of the error, unless I'm missing something from this question.
So the question is, you can get quantitative estimation of your error. You've got accuracy, you've got a number, but you're not sure if it misjudged the cat from the dog because it's similar to a cat, or it looks like a dog, but there's something in the background. So you don't understand the qualitative part of the error. Do you ever look into those errors your classifier makes and analyzes that? And do you have a habit for that?
I mean, I think it's almost always a good case. So that kind of falls into the second habit of like, visualizations and maybe investigating the data, but like after your classifier does the job. And yeah, I think it makes like really a lot of sense, and it helps you to uncover some like really stupid things.
Okay, so I think those are all of the questions. It was a really interesting talk.
Thanks.
And I believe we now have time for break. So I hear the organizers will send you coffee and cookies to your door. So please go check. And for now, thank you. And we'll see you in a teenage minutes. Thank you. Goodbye.